There is a question that can define the future of humanity. How can we feed more than 10 billion people without destroying our planet? While farmers continue to produce food in the way we've known for thousands of years, engineers and scientists are proposing something completely different. Artificial foods, farms controlled by artificial intelligence, robots that harvest fruit more precisely than human hands, lab-grown meat, foods created by algorithms, and even 3D printed steaks. All of this is already starting to challenge what we understand as agriculture. For some, this is the only solution capable of feeding the population of the future. For others, it's the beginning of a transformation that could put the world's food production in the hands of technology, and more precisely, in the hands of those who own these technologies. And the question is this: are we about to solve one of humanity's greatest problems, or are we just creating a new form of dependency? And there's more. And what if the greatest biotechnological innovation of our century to feed humanity were simply banned by law and treated as a crime against public safety? Let's understand this, friends. Hello, impressed ladies and gentlemen. I'm Realidade Impressionante, and you're watching Realidade Impressionante. Historically, we've kind of always been at the mercy of the seasons, the rains, and the quality of the soil. A single prolonged drought or an unexpected frost can destroy entire crops and cause significant increases in food prices. And this model that has sustained humanity for several centuries is now beginning to reach its limits in the face of population growth and rapid urbanization. To overcome these barriers, engineers began to treat food cultivation as a high-precision industrial process. Networks and sensors continuously monitor temperature, humidity, carbon dioxide concentration, light, and the nutrients dissolved in the water. Algorithms analyze this information in real time and automatically adjust each environmental variable, thus creating ideal growth conditions during all 365 days of the year, regardless of the weather outside. And this transformation is based on three major technological pillars. The first pillar is urban vertical farms. Instead of occupying huge stretches of land, these structures stack crops on dozens of floors inside smart buildings and do this using hydroponic or aeroponic systems, which completely eliminate the need for soil. Besides greatly cutting water use, this strategy moves production closer to major cities, reducing logistics costs and transportation emissions. The second pillar is the so-called agrobots. These robots move through crops using computer vision to individually analyze thousands of plants. Instead of applying pesticides, or rather crop protection products, over entire areas, the robots identify exactly where there is a pest or weed. In some experimental projects, high-precision lasers eliminate these invasive plants without using herbicides, thus reducing both waste and environmental impact. The third element is predictive artificial intelligence. Integrated with sensors distributed throughout the farm, it anticipates needs even before the first signs of stress appear in the plants. If a certain crop will need more nutrients just a few hours later, the system automatically makes the adjustments, keeping the cultivation very close to the ideal development conditions. But perhaps the biggest challenge of agricultural automation has been to reproduce something extremely simple for us: the human touch. Delicate fruits like strawberries, tomatoes, or peaches can be easily damaged by minimal pressure. To solve this problem, engineers have developed what are called soft robotics. Instead of claws or hands with rigid fingers, these arms use flexible pneumatic structures and soft materials, capable of distributing force in a way very similar to human fingers. At the same time, RGBD cameras, infrared sensors, and computer vision systems analyze much more than just the external appearance of the fruits. They identify the size, shape, coloration, and even characteristics associated with the degree of ripeness, allowing the robot to pick only the produce that has truly reached peak ripeness. At the same time, when necessary, smart sprayers target pesticides exclusively to the contaminated leaves, significantly reducing the use of these chemicals compared to conventional methods. This transformation also changes the very architecture of cities. Future urban biofactories will not operate in isolation, okay? They will need to integrate water reuse systems, nutrient recycling, and even the use of heat generated by servers, electrical equipment, and the climate control systems of the buildings themselves. While large crops like soybeans, corn, and wheat will continue to occupy vast agricultural areas operated by autonomous machines, much of the production of vegetables, greens, and fruits may move to these smart structures installed within urban centers. But humans don't just live on greens, right? We eat meat, a lot of meat, and this kind of food is already being produced in laboratories, okay? Shall we take a look at that now? Humanity has always faced an apparently inevitable challenge: producing enough protein to feed a population that keeps growing, and doing so without endlessly expanding the use of land, water, and natural resources. It's in this context that the idea of producing real meat, but without the need to raise or slaughter animals, came about. The promise was revolutionary. Using just a few cells taken by biopsy, it would be possible to grow tons of muscle tissue in large industrial bioreactors, all while consuming much less water, less land, and emitting less greenhouse gas. But instead of being welcomed as a solution for the future, this technology began to face strong political and economic resistance. The tension began to grow back in 2023 when different governments started to see lab-grown meat not just as a scientific innovation, but as a possible threat to the traditional food production model. Italy was one of the first nations to ban its production and commercialization, arguing that the measure would protect the country's food culture and also the activities of rural producers. Shortly after, some U.S. states followed a very similar path, creating legal restrictions that halted billion-dollar investments in a sector that until then was considered one of the biggest bets of modern biotechnology. To understand this conflict, we must first examine the engineering of cultivated meat. It all starts with a small sample of cells taken from a living animal without the need for slaughter. These cells are selected, multiplied, and fed inside bioreactors that carefully reproduce the conditions found in the living organism. Temperature, oxygenation, nutrients, and growth factors are all continuously controlled by automated systems. But producing just a cluster of cells is not enough. To form a whole steak, a cut of meat similar to what is found naturally, researchers use microscopic structures known as cellular scaffolds. They basically function as a kind of temporary skeleton that guides the growth of muscle fibers, allowing the tissue to acquire organization and textures similar to conventional meat. This approach drastically reduces the time needed to produce protein. While cattle take several years to reach slaughter weight, a batch of lab-grown tissue can be produced in just a few weeks in a fully controlled environment, without depending on climate, pastures, or large agricultural areas. And it's precisely this efficiency that raises concerns in different sectors. Many governments argue that a rapid adoption of this cultivated meat could have profound impacts on the entire livestock supply chain, affecting rural producers, slaughterhouses, transport companies, and thousands of jobs connected to the countryside. Another point that is often raised involves technological concentration. Since a large part of the processes depends on patents and highly specialized platforms, there is concern that only a few companies could control the strategic technologies for global production of food and, in this way, shifting part of the control from farms to large biotechnology groups. There are also ongoing discussions about the need for long-term studies. Although regulatory agencies carefully analyze each product before its approval, critics argue that much more data is still needed on the continuous consumption of these foods over several decades. Singapore, for example, became a pioneer by authorizing the commercial sale of lab-grown meat, while Israel is heavily investing in research and also in incentives to expand this industry. They've already made and eat their own meat there. Besides the food market, this technology also sparks interest in strategic sectors, including space programs. On long-duration missions or future colonies beyond Earth, producing protein in bioreactors could be much more viable than transporting large amounts of food or raising livestock in isolated environments. But there's something quite controversial related to lab-grown meat, and I believe you might not know about this one yet, okay? But hold on, I'll explain it to you. I'll tell you exactly how all of this works, and maybe it'll change your view about this technology, all right? Or maybe not, right? Let's see. Lab-grown meat was introduced to the world as one of the greatest promises of modern biotechnology, a proposal that seemed almost like an engineering miracle and would be able to produce real steaks without slaughtering any animals. The idea quickly attracted billions of dollars in investments and was sold as a revolution capable of transforming the global food system. But while this technology was making headlines and generating excitement among many people, one detail remained largely unknown to the general public. For those cells to multiply inside the bioreactors, many companies still depended on an ingredient that was obtained precisely from the industry they promised to replace. Taking a few muscle cells from a living animal is relatively simple, my friends. Today's engineering and technology can already do that. The real challenge begins afterwards. These cells need to multiply millions of times until they form enough tissue to produce food that's actually ready. Let me explain it better. Just like any cell in the body, these cells also need nutrients, proteins, and extremely specific biochemical signals. The goal is to keep growing in a healthy way, right? That's why they need all of this. And one of the solutions found by laboratories was to use what's called fetal bovine serum, known internationally as FBS. This material is rich in proteins, hormones, and growth factors capable of stimulating extremely efficient cell division. In practice, it became the culture medium most used in biomedical research and also in the first cultivated meat projects. The problem is exactly its origin. The serum is obtained during the processing of bovine fetuses from pregnant cows that were slaughtered. Although its use is quite old in scientific research, its presence within the lab-grown meat industry has created a huge paradox. A technology that was presented as an alternative to animal slaughter still depended, yes, to a large extent, on the traditional livestock industry itself in order to function. Besides the ethical issue, there was also another equally important obstacle: the cost. Producing fetal bovine serum involves a very complex process of collection, filtration, and sanitary control, making it one of the most expensive inputs in biotechnology. Depending on the purity and application, a single liter can cost thousands of dollars. And this, of course, makes large-scale production economically unfeasible. When this detail started to gain visibility, investors, consumers, and researchers intensified their pressure to find alternatives that are completely free of animal components. From then on, the scientific race began to replace serum with chemically defined culture media. Instead of relying on complex biological fluid, researchers began to individually identify which proteins, amino acids, vitamins, and growth factors were truly essential for those cells. Other teams followed different paths. Some explored proteins obtained from precision fermentation, using genetically modified microorganisms to produce molecules identical to those found naturally. Others investigated plant extracts derived from algae, yeast, mushrooms, and even soy, aiming to create much more sustainable and economically viable culture media. And these advances allowed several companies to announce processes completely free of fetal bovine serum. However, a new barrier arose almost immediately: industrial scale. Producing a few liters of these synthetic media for research is relatively simple, yes. Now, producing tens of thousands of liters while maintaining quality, stability, and competitive costs remains a huge challenge in chemical engineering, biotechnology, and also logistics. The larger the production, the harder it becomes to maintain the speed of cell growth without drastically increasing the final price of these products. And today, the sector is going through exactly this transition. The technology is already able to reduce its dependence on animal serum, but it is still seeking a balance between efficiency, sustainability, and economic viability. And tell me, my friend, just with the information we've seen so far, would you be willing to trade your natural food for artificial food? While you open the comments section and help me out, I'm going to show you something new about milk, something you probably don't know yet. Can technology already recreate this type of food as well? Let's check this out now. What if I told you that artificial intelligence discovered that mixing cabbage and pineapple can create the exact flavor of cow's milk? The development of plant-based foods has completely abandoned that traditional trial and error logic that chefs were using. And the idea is to turn exact computational science into something that can really change our society. By cross-referencing databases from two completely different worlds, generative algorithms are kind of hacking culinary chemistry to create the future of our nutrition. It all starts long before the cooking pot, you know? Researchers analyze animal-based foods using mass spectrometry and other techniques capable of identifying thousands of molecules responsible for the aroma, texture, viscosity, acidity, and the flavor we like. This information is then converted into huge chemical databases, which become a reference for the algorithms. From there, artificial intelligence looks for plant-based ingredients that may share similar molecular properties, even if traditional human cooking has never used them together or mixed them like that. That's exactly what sets the algorithm called Giuseppe apart. It was developed by Notecole. Unlike a human chef, it doesn't have cultural references or creative limitations. Its job is simply to compare chemical structures and predict how they will interact during industrial processing. The system evaluates thousands of plants simultaneously and calculates how each protein, fiber, sugar, and aromatic compound will behave under different temperatures, pressure levels, and preparation methods. In this way, the AI can continuously refine its predictions based on feedback from human experts. That's how the combinations considered highly likely came about. To produce characteristics of traditional milk, the AI identified that compounds found in pineapple and cabbage, when combined with other plant-based ingredients, helped build a sensory profile very close to cow's milk. In another project, chickpea proteins and bamboo fibers were used to reproduce the creamy texture that we see in ice cream. In the development of plant-based burgers, ingredients like cocoa and spinach helped simulate meat's characteristic flavor, and even its color changed during cooking. See? The impact of this approach goes far beyond culinary creativity. Companies report that the time needed to develop new foods has dropped from several years to just a few months, while the consumption of water, energy, and raw materials has also been greatly reduced. According to experts, artificial intelligence proves that the secret to feeding the world sustainably is not in expanding pastures, but in decoding the molecular code of the plant kingdom. The cuisine of the future is now written in lines of code, my friends. And when you combine artificial intelligence with robots to produce food, do you know what happens? Let's check this out now, okay? Subscribe. Producing food has always meant relying on land, the seasons of the year, and also human labor. Today, this logic is already starting to change. The most advanced farms on the planet no longer operate as rural properties, but as true automated biofactories, where artificial intelligence, robotics, and genetic engineering work together to control every stage of cultivation. The goal is no longer just to produce more food. Now, the aim is to turn agriculture into a continuous, precise, and almost autonomous industrial process. In the most modern facilities, sensors distributed throughout the environment continuously monitor temperature, humidity, lighting, and nutrient concentration. Each plant receives a kind of digital twin, which is basically a virtual replica updated in real time, allowing algorithms to predict its growth and correct any deviation before it even becomes a problem. Instead of workers walking through the aisles, robotic platforms and autonomous vehicles transport the growing trays to the inspection, harvesting, and packaging modules, thus creating a flow similar to that of an industrial assembly line. And artificial intelligence no longer relies exclusively on the cloud. Processors installed directly on the robotic arms analyze the images in fractions of a second, identifying the exact point of ripeness for each vegetable. Researchers have already created systems that can replace natural ecosystem functions. Small drones and electrostatic devices carry out pollination in enclosed environments, while artificial intelligence models assist in the development of plant varieties specifically adapted to automated cultivation, prioritizing productivity, flavor, and nutritional value. And the next challenge is to make these biofactories energy independent. The combination of high-efficiency solar panels, advanced batteries, and local energy reuse systems. It could allow crops like wheat, rice, and soybeans to also move into fully controlled environments, thus expanding production without the need to put pressure on new agricultural areas. Robotic farms have ceased to be just a niche alternative and can now become the backbone of humanity's future. And by practically rewriting the laws of agriculture, biofactories turn food into pure data technology, optimizing cultivation with the precision of a high-tech factory. A practical example of this can be seen in this next point here. Take a look. When you think of picking fruit, you picture an apple, right? But strawberries, for example, seem easy for anyone, don't they? But for a robot, this is one of the most complex operations in all of agriculture. Just apply a few grams of force more than necessary and you'll crush the fruit, turning it into almost a puree or juice. If this tragedy doesn't happen, another problem would be reducing its shelf life and turning a high-value product into pure waste. And all this delicacy is what prevented the complete automation of fruit farming. Now, a new generation of agricultural robots promises to change this. While industrial robots have been working for decades handling metals and rigid parts, fruits represent a completely different challenge. Each one has a unique shape, size, and position, often hidden among the leaves and branches. To solve this challenge, engineers created a platform equipped with up to 24 robotic arms that are independent from each other and capable of working simultaneously. Each arm has its own high-resolution cameras and optical sensors. This way, they can individually analyze each fruit before deciding whether it is ready for harvest or not. If the system finds green areas or incomplete ripening, it moves to the next one. The machine's secret is avoiding the fruit's most sensitive part. Instead of squeezing the strawberry to pick it, the claws hold only the small stem that supports it. From there, an integrated blade makes a precise cut, allowing the fruit to be gently guided through padded channels to the packaging, reducing damage caused during harvesting to almost zero. In addition, the system can work throughout the night, when lower temperatures can help preserve and maintain the quality of the strawberries. The Agrobot E-Series shows that agricultural robotics has finally begun to master one of the greatest challenges of automation: handling living organisms with a delicacy that, until recently, seemed to be a uniquely human ability. And speaking of pushing boundaries, my friends, just imagine food being produced entirely by a machine, coming straight out of the machine as ready-to-eat food. Have you ever thought about that? Have you? Can you picture it, did you? Let's see then if your imagination matches reality. Thank you. Well, forget about plant-based burgers, lab-grown meat or nuggets, sausages, or other ultra-processed foods we have nowadays. Food technology has already broken the most complex physical barrier in gastronomy, creating whole cuts, that is, entire steaks, without touching a single animal. But recreating a whole cut with muscle fibers, distributed fat, and a texture similar to steak, until recently, seemed like an impossible challenge. But this obstacle is being overcome by a technology that was born in industry and made its way into gastronomy: 3D food printing. Layer by layer, high-precision printers deposit plant proteins in carefully calculated patterns to reproduce the architecture of animal muscle. And it's worth noting that the bio-ink used needs to be fluid enough to pass through the printer nozzle, but it also has to harden immediately after deposition to maintain the shape of the food. Basically, instead of using plastic like conventional printers, these machines work with different food formulations. The first one is made up of proteins extracted from peas, soy, or microproteins derived from fungi. These are responsible for forming the fibers that simulate muscle tissue. A second formulation combines carefully emulsified vegetable oils to artificially produce something similar to intramuscular fat. This is responsible for the juiciness during cooking. Delicious meat. A third mixture adds natural pigments and minerals that give that reddish color characteristic of raw meat, and they contribute to the flavor during cooking. This technology is beyond the experimental phase. Companies like the Austrian Revo Foods sell plant-based fillets printed in 3D that reproduce the appearance and texture of salmon, for example. Meanwhile, the Israeli Hedefin Meat supplies structured cuts to high-end restaurants in several countries, using digital models capable of organizing each layer of the food so that it reacts to heat in a way similar to traditional meat, thus developing aroma and texture very similar to real meat. Yes, my friends, we may now be witnessing the greatest food revolution since the advent of agriculture. A future where robots farm, artificial intelligences create recipes, laboratories produce proteins, and biofactories supply entire cities. And they really can help us feed a population that has never stopped growing. At least until now, right? But every great revolution also changes who controls humanity's most important resources, doesn't it? And maybe in the future, our biggest challenge won't just be producing enough food to feed everyone, but deciding who will have the power to produce that food and how it will be produced. And to what extent will we be willing to trade the natural for the artificial? And in the end, who will decide what ends up on our plate, huh? Can you tell me? The future hasn't been chosen yet. There's still a lot to happen, and a lot is still up in the air, right? And maybe that decision about what our future will be like actually starts with the choices we make now. So leave your opinion here in the comments, okay? That really helps the channel and also helps other people make good choices about what they're going to consume from now on. If you like this episode, go ahead and leave a like and make sure you're subscribed. Click on one of the 2 suggestions on your screen, and we'll see each other soon. It's quick. Just click, and I'll see you there, okay? Thanks for staying with me. See you soon. I'll be waiting. Thank you.